contained in W, the weight little w of f. Oh, sorry, with multiplicity. With multiplicity and w is the absolute value of the Mobius function in W to V. Okay, I'm a bit confused. I think Rn will itself come as an element of the poset, and I mean of the lattice, and this is -1 to the codimension of W in Rn times mu of. Okay, so that is the multiplicity. So so this will follow from that theory. Okay, I've skipped lots of details. So what was the argument yesterday? So it projects.
The data algebra is, I mean, it's idempotent and abelian, right? The things it projects onto the lattice algebra.
Yeah.
Which consists of idempotent.
No, but why does this action factor through that?
That she proved that. No? That's why the whole thing is that. Pooja's lecture. CS to CL is the operator from S to L with gives us the projection from.
That's fine.
And then the kernel.
That's fine. All that is fine. But the action has to factor through that for it to be a diagonalized.
But she said she could show it. No, she didn't. I don't think she proved it, but she said she could prove it. You remember she said that I first thought that diagonalizability is hard, but then I realized I could do it. She said something like that, but she didn't prove it. But she said it can be proved without too much work.
No, extra. In some cases. Under some.
The W also.
Huh. But here I think this this is not the full class of LRBs, right? I mean, these are hyperplane walks, so maybe the condition is satisfied over here. That's what I thought when I was.
In this, what is the Zetlin library example?
I'm going to do it. That's why I don't have much time. So I want to quickly state all the results. And okay, so before I state, so I want to state something about the mixing time, which is what we have been sort of obsessed about. So say that W. Okay, so the probability distribution W on F is separating if for all H in A, for all the hyperplanes, there exists, oh sorry, okay, there exists looks like F. So there exists F in F with F not contained in H and WF greater than 0. Okay, so for each hyperplane there you can find some face outside of it where there is some which has some non-zero probability. So the second theorem is about separating. So the first, so this in this class, in this level of generality, this process is not so interesting probabilistically because it's not irreducible. So the first statement here is that P has a unique, or let's say CT has a unique stationary distribution. So this Markov chain has a unique stationary distribution if and only if W is separating. Okay, so this separating assumption make sure that the process is interesting. So there's non-trivial probability everywhere. And so now assume for the other two parts that W is separating. So now we can talk about things like mixing times and so on. Okay, so here's the really nice property about these left regular bands that Pooja didn't discuss, but it's sort of very, it's a nice property and it's very useful also. So you sample without replacement from W to get an ordered sequence of phases F1 to Fm such that F1 etc. up to Fm belongs to C. Okay, so you keep sampling phases. So without replacement means you don't sample the same phase again. So you keep sampling using the distribution W. You keep sampling until the product F1 to Fm is now a chamber. Okay.
Product is from F cross C to C.
Well, okay, that's true. So you can also define product of phases. Okay, so which I didn't do, but so you can also do that, and you can keep sampling until you hit a chamber. Okay. So let me call this product C. Then C has, let me call this unique stationary distribution pi. Pi is not good. Okay, let it be pi. Then C has distribution pi. Okay, so what is happening is, so there's this ordered structure. So you have first nothing, then you have some phases, and you keep multiplying by the phases. You go up until you are in the chambers over here. So these are the chambers, right? So you keep multiplying. You get phases, 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 phases. At some point, you hit the chamber. The probability of hitting any particular chamber is exactly the stationary probability of that chamber. So you see, we are doing two different things. In one case, we are looking only on phases, and we are multiplying phases until we reach some chamber. Okay, that'll always happen if W is separating. Huh. Phases are boundaries of chambers.
No, but when you say they are semi-group, you're thinking of them as functions on chambers.
Semi-group is on FUNC.
Yes.
That's how you compose them, right? So that's how the semi-group comes.
No, so this is, I mean, if you want an example, think of the free left regular band that Pooja defined.
What you said correct?
What?
That the product of phases comes by their action on chambers.
No, I think it's more general. So let me give you an analogy. So you remember the free left regular band.
Yeah.
So the free left regular band was actions, was defined on x1 to xk, was tuples where none of them are equal. And you keep multiplying, and there was a multiplication operation defined there, right? So you keep multiplying.
What you with this? Because then we went the other way. You defined the action in general, and then you said that the chambers were certain special ones.
So it's the same thing here.
Come from
Yeah, I know.
arrangements, I guess you have to go the other
No. Well, again,
I
I'm.
have one possible proposal. Maybe it happens that when you keep multiplying that, whatever C you put there, you will get the same chamber on the end. You have F1, F2, Fm. Not any C will give the same chamber. If that happens, then you can call that.
So you need to check that.
Yeah.
It becomes a linear rate. Its image becomes singleton. Then
Yeah, that's possible. Yes.
that, if that is the meaning, I can make sense of it. Otherwise.
Okay. But I
So that
it might also be possible to make sense of products of faces in the sense of the free left regular band, in which case the chambers are the
But
permutations.
in the context of hyperplane arrangements, that at least you haven't told us.
No, I haven't. No, I have not claimed that I have to do it. So, yeah. So, can I take 5 more minutes?
Yes,
I want to
yes,
connect
yes,
to the.
yes, yes,
I
absolutely.
want to connect to the Zetlin library. Okay. So assuming this statement can be made sense of, what you can do is you can multiply faces until you reach a chamber, and you choose faces according to the distribution W. The moment you hit a chamber, you have the probability of that. I mean, you will hit a chamber with its stationary probability.
The first time you did it.
The first time you hit it, you will exactly hit it with its stationary probability. So this thing is what allows you to estimate the mixing time. So the total variation distance between p to the k and pi is bounded by the sum of the hyperplanes in this hyperplane arrangement, lambda h to the k. So h is itself going to have an eigenvalue over there. So h belongs to the intersection lattice, and so this will give you the total variation distance estimate. This from B you will get something like this.
Here you have to multiply in the other way.
That's right. Yes, exactly.
Then the image is decreasing. It becomes
Yeah. So here we are.
What do you mean by
So here I'm multiplying on the right, but my so what do you want to say? So when we do the
I understand. Here the F2 goes on in between the.
yeah, right. So C goes here to F prime C.
the image is decreasing.
See that portion is a reverse inclusion.
I think the way this is written, it's inclusion. No, this is inclusion because you see Rn is on over here, is on the right. Huh?
So you
So
want chambers at the top, phi we include.
yeah, right. We want the chambers at the top. I mean, the way I have sort of given a heuristic picture. Okay, so let me connect to the Zetlin library. So 2 examples. So the first is, so many known class of walks fall into this very broad framework. The first is this Boolean arrangements. So this is what Amri was asking. So here you take the coordinate hyperplanes. Hi is the hyperplane xi equal to 0. So in Rn. Okay, so if you do that, so for example, in R2 you have these 4 chambers, C1, C2. So you have the quadrants. In general, you have the orthants, right? So we have a random walk on this, and you can have a very general random walk. But and you can index each chamber by a binary word. So because each chamber corresponds to some coordinate being positive and some other coordinate being negative. So these are chambers. So C is in bijection with +1, -1 raised to the n. So, right? In a very obvious way. And now you can choose any fancy probability distribution on the faces, which are now the coordinate axes and the origin. So the size of the faces is 3 to the n, because you can have zeros also. So you can have +1, -1, and 0 if it's a coordinate axis or a hyperplane itself. And then, okay. So let's see. So if you take W to be uniform on the rays, so if you do that, then we get a random walk on the hypercube. So this is the same as the random walk on the hypercube with laziness probability a half. So with probability half you stay there, and with probability 1/4, well, you have 1/2 to the n, and so there's like, so this is a walk on that thing. So moreover, if we consider the number of ones, if we consider a Markov chain on the number of ones, we get the Ehrenfest term. Okay, so we can get the Ehrenfest Markov chain this way. So the other thing, the other example which Murli asked is you consider what are the Weil chambers for Sn. So you consider the following Hij's to be the set where xi minus xj is equal to 0. Okay, in Rn. Right? So okay, I'm not going to write because it's okay. But if you do that, then the chambers exactly are indexed by are in bijection with permutations, because all chambers mean none of the coordinates are equal. That means there's an ordering. So if there's an ordering, they belong to Sn. Okay, and then if okay, so I don't say it. So you can choose. Then it's a bit complicated to write. One can choose W to get the Sutton library. Oh, sorry, I'm well over here. And let me end with the total variation estimates. So if the xi's that I had today, if we set xi to be 1/n, so that's the first example I did today, then one can show, I could also write down the total variation distance estimates here, but I'm not doing it for lack of time. dTV of whatever the Markov chain that I called it, I don't know, xk is less than or equal to n/2, 1 minus 2/n to the k. So if k equals n log n plus cn, we get e to the minus 2c by 2. One can also show, using a separate argument, that if k is n log n minus cn, oh sorry, this is n log n, then dTV, so c positive, yeah? Then dTV of xk and pi is close to 1. So again we have a cutoff. So that's the picture. Okay. So I'll give you some idea about this tomorrow. So for tomorrow, the plan is that I'll define the transpose of this. At some point, somebody asked me about transpose, so I'll do the transpose of this. That is the top to random shuffle. So the Cetlin library is random to top. So this is the top to random shuffle, and the random to random you can think of as a composition of the two. It's a random to top followed by a top to random. So I'll do that tomorrow, and I'll show you. There's lots of connection to representation theory, and there's some recent progress that that one can hopefully improve on. Okay. Any questions? Sorry, I'm well over time.